Thank you very much for inviting me here. It's my great pleasure. I promised my sons that I will give them best regards because it's live streaming. So let me start. The title of the talk is Synthesis and Superconductivity in Novel Compounds. My obsessions are new superconductors, but I love everything what is new. So let me start with the outline. I will start with the introduction. Then there will be part about the synthesis, then the crystallographic. Sorry for the typo, physical properties, and I will finish with the summary. So I am quite often asked, how do we search for new compounds? How do we find new superconductors? And here is the matrix. I will show you a few examples. All the examples come from my laboratory, from Gdańsk University of Technology. So what we do, first of all, we check the database. There are 4 strategies that are shown here. So depending what is known or unknown in the system. So you can see that there is a structure type, chemical compound, and physical properties. So if everything is known, you can ask me, what are you looking for in such a case? But actually there is a lot of things to be done, and I will show you in a minute. Then another strategy is if the structure type and chemical compound are known and the physical properties are unknown, the next one is as shown, and finally, you know nothing. So Paul Canfield used to say unknown, unknown, or known, unknown, and so on. So it's pretty much the same. You know this person for sure, at least you know the story about him. I am too young and still old, but I have never had a chance to meet Bernd Matthias, of course. But he was a superconductor hunter during 1950s, 1960s, and here is his paper. 1 page, just 1 page physical review paper. 8 superconductors reported in the same paper. No figures, no superconducting properties. That's exactly what I am showing here. Everything is known, but we were interested in just because there was no superconducting properties for calcium bismuth 2. And besides, Tc seems to be strange, 1.7 Kelvin. And another thing is that there was a theory paper published in this scientific reports, and theorists expected Tc as high as 5.16. So it's way higher than 1.7 in Bernd Matthias' paper. And my student who is sitting here, now he's not my student, he's already a PhD and DSc candidate, grew crystals. And as you can see, calcium bismuth 3 looks like that. Of course, it's strange because calcium bismuth 3 is supposed to form in a cubic phase, so it's not a cube. And besides, another point which is strange is that the fact that we are way above the Long-Petit law. So we checked the EDS, and it appeared it's not calcium bismuth 3, it's calcium bismuth 2. But still, it's a superconductor with Tc 2.2. It's a very interesting superconductor because the bismuth forms the square lattice, and because it's a 2-dimensional superconductor. The paper was published. I think it's like 5 years ago or so. Another 3 examples of this strategy, everything is known, is lithium bismuth, cerium iridium free, thorium iridium free. So there are a lot of things you can be done with a strange strategy that everything is known. Another example, but now we have a second strategy. So structure type is known, chemical compound is known, and paper is already published in a PNAS, Proceedings of National Academy of Science, and the title is Structure of Super Hard Tungsten Tetraboride. The paper was published by UCLA group, and fortunately to us, they have not measured the low temperature magnetic susceptibility, and we found it's a superconductor, so the title is Superconductivity in the Super Hard Boride WB 4.2. Okay, then I think, I'm sorry, okay. Another example could be lithium palladium to germanium and lithium palladium to silicon, but actually Dr. Michał Winiarski is going to give a talk about this tomorrow at 5 p.m. in Hall 2, so I just skip it. The strategy number 3, structure type is known. So we know the structure type, and we replace 1 or 2 atoms, or 3 atoms. This is a paper from 1997. 1997 from Bell Lab. Bob Cava published a paper about lanthanum-3, copper-4, phosphorus-4, O2. And a few years later, when all these iron arsenides were published or studied, I went back to this paper and I found that possibly copper can be replaced by nickel. And we made lanthanum-3 nickel-4 P4O2 with TC 2.2 Kelvin. Okay, TC is low still, but anyway, that's another example, another material in this big family of the iron oxy arsenides or iron arsenides, nickel arsenides, and so on and so on. Now, I smoothly go to the titled compound, and still, this is the same strategy. So the structure type is known, but we want to do something else. So niobium iridium 3, the gold copper 3 crystal structure type, this compound has been studied. There is no superconductivity, fine, and we ask ourselves, it's possible to put a small atom like boron inside this octahedra, And my former student melted several samples, and here is the X-ray diffraction pattern. So what you see here is the mass. There are a lot of reflections. Too many reflections to say that the sample is pure, of course. But nevertheless, we found that there is a main phase. The main phase is a cubic phase, which is shifted, fine, which is actually very good because the lattice parameter is larger. But there are extra reflections, and most important is the fact that there is a superconductivity at 7 Kelvin. So question is, what does superconduct in this system? As you can imagine, this is a rather expensive experiment because of the iridium, but nevertheless we decided that we want to make more and more samples, and what we call it's just the, going through the phase diagram. So the first point is here. Okay, this is my first point. Second point was here, and another point was here. This point is 113 or 131 if you wish. That one was 122, and another one was 479. And what you do, you compare the X-ray diffraction patterns, and also, and actually that's actually even more important, you compare magnetization. This is the normalized magnetization. You see it's EMU per gram. And you can clearly see that the strongest signal is here. So is it 479? Maybe. And here is the X-ray diffraction of the 479. You see that those impurity peaks now are much much higher, and the main phase, which was the cubic phase, is actually gone, almost completely. It's almost completely gone. We tested more and more samples, and this is the fourth strategy. Nothing is more known. And here it's a first conclusion. or actually the first question. Do we have the same crystal structure which we observed for rhodium-based compounds, 1, 2, 2, niobium, rhodium, 2b2? That paper was published 4 years ago, and this is the chiral crystal structure, non-centrosymmetric, fine, the same composition as this sample, so we thought maybe it's the same crystal structure, but it appeared that it's not the same crystal structure. From the very beginning, we knew it's not the same crystal structure, and without the help of Wei Xie and her student, we couldn't move to another point, to another level. Without the help of the crystallographers, we couldn't find, or we couldn't refine this crystal structure. So the first proposed model was C2 over C, which is the space group 15. They confirmed stoichiometry, 1 to 2. They confirmed it's a monoclinic stoichiometry, but centrosymmetric. And actually, we didn't like it. We didn't like for 2 reasons. And the first reason is that we already observed very high upper critical field. For the centrosymmetric, just the typical BCS superconductors, you cannot go above the Pauli limit, which was actually our case. And second thing is that when you get the crystallographic table, what you do, you try the Rietveld analysis of your powder X-ray diffraction, and it didn't work. So we asked for the other model, and another model which came to us was the model in which the space group is even lower. It's number 9. So monoclinic, still monoclinic, and non-centrosymmetric. And that one, as you can see, worked out. So it works like that. Without the crystallographers, you cannot go to the next level. But what you do, when you get the crystallographic table, you have to go back to your powder X-ray diffraction and try Rietveld analysis. And Karolina Górnicka did this, and you can see it's pretty much what you expect. There are some impurities, small impurities, but this is confirmation of the crystal structure. How does it work? How does it look like? Well, it's complicated. It's very complicated. So I'm not going to details, but the most important point here is that we have the boron-boron dimers. Boron-boron dimers, you see that the distance between boron atoms is only 1.7 angstrom. And even more, the boron-boron dimers, they are aligned different directions. So this is the system we worked on with iridium. And you can ask me, is there any link between this 1-2-2 system and that 1-1-2-2 system with rhodium? And there is a link. The link is that we have a different stacking. Here is XY, here is XYZ. Okay, so either 2 stacking layers or 3. And that one is non-centrosymmetric, monoclinic crystal structure. That one is chiral, trigonal, of course, non-centrosymmetric crystal structure. Both are superconductors, and they have a very similar superconducting properties. Now, let's go to physics. So first is resistivity. And you can see that there is a clear transition. Great. So there is a transition to superconducting state. Then we have, we plotted upper critical field as a temperature. And of course, we finished at 9 Tesla. I will show you more points in a minute. Nevertheless, the upper critical field you can obtain from WH theories like it's about what? About 16 Tesla, which is way above the Pauli limit. For the tantalum compound, it is 14 Tesla. Here is almost 9 Tesla. So it's above Pauli limit. Magnetic susceptibility. Magnetic susceptibility shows the Meissner fraction. The transition here is very sharp. For the tantalum sample, it's not so sharp. Now we have better samples. And what is striking here is when you plot lower critical field as the temperature, in this feat, usually you just take you just take 2. Okay, n equal to 2. But in this case, we must have like close to 4. It's 3.8. How much time do I have? Okay. For tantalum, iridium 2, boron 2, the power law is 2.5, so it's close to 2, but in this case it is almost 4. We don't know what is the reason of that. Actually, we observed that such a high value of n only in 2 cases, and that's one of the case. Heat capacity. Heat capacity data is shown here, so you can see Cp over T as a function of the temperature. So there is a clear anomaly, and in case of niobium-based sample, clear anomaly in case of tantalum sample. When you apply magnetic field, you can at least suppress superconductivity, not perfectly suppress, but still. You can get gamma value, which is 4.9. In this case, it's 5.2. So we can say there is not much difference between the gamma. And the Debye temperature is 274 and 230. So the Debye temperature is lower in case of tantalum-based compound, which of course is what you expect, because tantalum is heavier than niobium. But most important, and actually the most interesting feature is here. So you can see the data in a superconducting state. It's a zero field measurement, and well, still the TC is 7 Kelvin, so you can try fitting the data using different models, and you can see 2 models. One is just a single gap, and the other is just the power law. Fine. So as you can see, the power law looks pretty good. Actually, looks very good. And in 2019, so 3 years ago, tungsten-free aluminum 2 carbide was published in a Physical Review B, and there is also the power law. Okay, there is also the power law fit proposed by the authors. And well, I thought maybe that's what it should be. But the same data, okay, the same fits. So the blue one and the red one. And what I will do, I will change the linear scale to logarithmic scale. And big surprise, the power law doesn't work. Not at all. But you cannot see it. You cannot see it when you plot it as a linear scale. So you have to be very careful if you see that the power law works, the power law fit of the heat capacity works for your compound. It's good to plot it as a logarithmic, in logarithmic scale. Okay, so is it just single gap superconductor? We checked the other option, which is just S plus S wave, so 2 gaps. And the 2 gaps, here you see the 2 gap model, seems to be much, much better. But Zach Fisk a few years ago and Joe Thompson told me the same thing. You can add another gap and your fit will be even better, which is of course true. So it's not a proof that I have multi-gap superconductor. We proposed it's a multi-gap superconductor based on the density of states calculations and so on and so on. But I am not convinced it's a 2-gap superconductor, especially because 3 weeks ago we published a paper in PhysRev B showing the muon spectroscopy that actually 1 gap is much better fit. Okay, let me go back to this picture. 2 gaps, 2.42 millielectron volts, 9.1 millielectron volt, the same values taken for the fit, and this is that line. It doesn't work. It doesn't work at all. So most likely, niobium iridium 2 B2 is a single gap superconductor, unfortunately. However, oh, by the way, here is also the high magnetic field data collected in Tallahassee. So you can see that it's a linear, actually, behavior up to pretty much 16, 17 Tesla to the very low temperature, 0.32 Kelvin. Okay, so comparison of those 4 superconductors comes in this slide. So you have niobium, iridium 2, boron 2, tantalum, iridium 2, boron 2, and the same but with rhodium. Tc is lower for the iridium compounds, 7.2, 7.6, 5.1, 5.8, and so on. So upper critical field is always above the Pauli limit, as you can see, 16 Tesla, 13 Tesla, 15 Tesla, 10 Tesla, 18, 14, 11, or almost 12, and almost 11. The anomaly of the heat capacity, so the heat capacity jump is like almost free, strongly suggesting strong coupling superconductivity. For the tantalum iridium 2B2 is pretty low, it's the lowest one, but still above the BCS expectation. Here is 1.6, 1.56. I am summarizing what I'm going to say. Why are the non-centrosymmetric superconductors important? And is the lack of center symmetry enough to be excited about them? Well, it is not enough. It is not enough. You need also the spin-orbit coupling effect, which should be strong to observe interesting physics. And there are not many. Actually, there are only 2 models or systems in which you can tune spin-orbit coupling. This is the first one. And this is the oldest one. Lithium 2, palladium 1 minus X, platinum X 3, and boron. So replacing palladium by platinum, you just make the spin-orbit coupling stronger, and you, at least we hope, or they hope, that this spin-orbit coupling will introduce the spin triplet superconductivity. There are some controversy, but I am not going to details. Another system, rather recent system, is molybdenum or tungsten free aluminum 2 carbide. And again, tungsten is much heavier, so spin-orbit coupling should be stronger. Molybdenum is much lighter, and you expect that the effect will be much stronger, as I said. So far as far as I know, there is no studies published, with the solid solution of the compounds. So we have 2 systems, and this is another one. Those 4 new superconductors, Bob Cava and also my lab reported or just discovered. Niobium rhodium 2 B2, tantalum rhodium 2 B2, that's the chiral structure. Niobium iridium 2 B2, tantalum iridium 2 B2. This is a monoclinic superconductivity, monoclinic crystal structure type. For niobium rhodium 2 B2, the group from Warwick University from the UK, they already published the paper showing that there is a single or maybe multi-gap, that's the conclusion, tested by, as I said, by muon spectroscopy. A few weeks ago, the Barhan Das published a paper showing that in niobium iridium 2 B2 there is a single gap superconductivity. Tantalum rhodium 2 B2 was tested again by Warwick group, and they found multi-gap superconductivity proved by muon spectroscopy, and we don't know about this one. We are waiting. Maybe soon we will be able to tell you about tantalum iridium 2 B2. But when you take a look on this picture, you realize that that one is actually the heaviest one, right? Because you go from niobium to tantalum, and you go from rhodium to iridium. So all the elements that are important for the superconductivity are there. And we hope that one will be also multi-gap superconductor. Okay, so almost the last one, the acknowledgments. I would like to thank Karolina Górnicka, who was responsible for this project, Michał Winiarski, who is part of my team. We also worked together with Shintaro Ishibata from Osaka University, Bob Cava, Princeton, and Weiwei Xie. Now she's at Michigan State University. We have also a big support from theorist Professor Bartek Wiendlocha from AGH University. And let me finish with this one. I guess there are no participants from Ukraine on here, but not many people actually. But let me say that if you do not read it, it means that we are with you. We do support the Ukrainians. We are looking for students from Ukraine, PhD students from Ukraine, and I strongly suggest that you do the same, because it's really bad time for them. Thank you very much for your attention.
Okay, thank you for nice talk and being on time. So this talk is open to questions. I think there is already one over there.
Oh, here. You were expecting something online.
I'm trying to go back to this.
Okay. Many thanks for a nice talk. I fully agree with your conclusions, because we have been studying also some non-center symmetric superconductors, and we unfortunately found that it's a necessary condition for finding something interesting, but not sufficient. So sometimes we find, but just to further to comment on your results, there is also an advice, perhaps, that we have seen that we have done experiments with exactly as we did with changing heavier and heavier elements, and we didn't find any effect. Why? Because we realized a posteriori, which means later, that by DFT calculations, these were not influencing mostly the Fermi level. So you should check before who is the major player in the Fermi level. This is a good advice, I think, because sometimes one expects something and finds something else. Now, a very general remark or question. Have you considered, because you showed how you try to find interesting materials, have you considered this, how it's called, new machine learning? They are developing a lot of strategies to find what might be interesting. Have you considered also this? Or?
Yes, of course, and many times. And I also got a lot of emails from theorists that must be a superconductor. But believe it or not, none of them was true. But the other way, when you find a superconductor and then you send the information to the theorists, there is always the reply, of course it's supposed to be a superconductor.
Okay, so any other question over there?
About your measurements, penetration depth measurements, you said that you had only one gap. Do you have some ideas about the symmetry of the other parameter in the material? I'm afraid that I can just send you this paper so you can check details of the muon spectroscopy. I will be happy to do it. Okay, just another thing about your critical field measurements. Do you have some ideas about the direction of the field, about the crystallographic planes or something like that?
Well, I would love to grow crystals, and we tried a lot of times. But the problem is that this is so complicated system that you cannot grow the crystals, so far, at least so far. And unfortunately, it is also expensive because of the iridium. So we are trying, but so far, what we can get polycrystalline samples, and believe or not, it was also very difficult. There is a very, how to say, not so wide or very, the temperature region in which that compound actually can be formed is very low, okay? Because, well, you see, it's just 1, 2, 2. So I'm pretty sure that many years ago, before I was born even, people tried to arc melt it. But you cannot control temperature of that sample during that process. Now we know that the samples cannot be obtained by just simple arc melting. And that's why we found them. We just made them using the solid method. Okay.
Okay. So any other question? Then I have a very quick question. So one time you showed upper critical field as a function of temperature, and then also the one that you measured at high magnetic field.
Yes.
So it looks like it shows linear behavior all the way to 0 Kelvin. I think that's very unusual, like possibly indication of maybe plus superconductivity or maybe multi-gap superconductivity. So like, have you thought about the possibility based on the upper critical field measurement?
Can you show? I cannot use it actually, for some reason. Okay. Yeah, exactly. So can you go back? More. Stop. The other way. Okay. Thank you. So thank you for this question. So I actually should explain what we have here. So this is the Ginzburg-Landau fit. Just a typical fit, just showing that it doesn't work. That's the fit with the power law. And the power law is like 1.1 as far as I remember. And now, going back to your question, why it's so linear? Well, one of the explanation based on the, the models Ruslan Prozorov studied in some time ago is that it's just a multi-gap superconductor. Just the multi-gap superconductor. We don't know. Actually, we showed that this is not the multi-gap superconductor, but there might be also some anisotropy effect. From the other hand, it's not a crystal, right? So it's open question. But nevertheless, this is what we observe. For us, the most important is the fact that the upper critical field is actually even higher than obtained from the WHH theory.
Okay, thank you. And I think before, would you like to give him certificate of excellent presentation on behalf of the organizers? Okay.
Thank you very much. Thanks a lot.
Thank you.